So let's move on to example 3. In this example, you have two functions, y1 equal to cosine of 2t and y2 equal to sine of 2t. And they are the solution of the differential equations, y double prime plus 4y equal to 0. Can you find the Wronskian of y1 and y2? So the Wronskian for two functions is going to be w of y1, comma y2 is equal to the determinant of y1, y2, y1 prime, y2 prime, and y1 in this case is equal to cosine of 2t, and therefore y1 prime is negative 2 times sine of 2t. And y2 is equal to sine of 2t, and y2 prime is 2 times cosine of 2t. And you're going to use the 2 by 2 determinant to calculate this Wronskian, so that could be cosine of 2t times 2 times cosine of 2t minus negative 2 times sine of 2t times sine of 2t. Right. And then you can combine them together. So cosine of 2t times cosine of 2t, you get cosine square of 2t, or this is 2 times cosine square of 2t. And sine of 2t times sine of 2t, you get sine square of 2t. And also you have negative here and negative here combined together, you get positive term. So added with 2 times sine square of 2t. And you can take 2 as a common factor, and you're left with cosine square of 2t plus sine square of 2t. So this is a trig identity. This is going to be equal to 1. Therefore, the Wronskian for this two function y1 and y2 is equal to 2 in this case. So the idea of the Wronskian different from 0 to show that the two functions are linearly independent or they form a fundamental set of solutions. Okay, now we're going to do something similar in example 4, but for different functions. So I want to show that e to the lambda t times cosine of mu t and y2 in this case is e to the lambda t times sine of mu t. So this look like some just random functions that I give you in the example, but later on in the lecture you will see this functions come up in the solutions of differential equations. So in this case, for example, for this two functions will pop up in the case where you have something called the complex root of the when you use the method of characteristic. In example 3, you will see something similar to that extent. That is, these are the solutions of a differential equations where you have to use something called the method of characteristic, and this fall into the complex root category. So for example 2, these are the case where you have two distinct root roots, R1 and R2, for the characteristic equation of the second order differential equations. But that's for the next lecture. But for now, I just want to ensure that this function will pop up again in all the lectures. Alright, so let's do example 4. Again, you have two functions, y1 and y2, and you want to show that they form a fundamental set of solutions where mu is different from 0 and lambda is also different from 0. This indicates that you want to find the Wronskian of these two functions. So again, the Wronskian formula is going to be the determinant of y1, y2, y1 prime, y2 prime, where y1 is equal to e to the lambda t times cosine of mu t. And y1 prime, so you take the derivative of y1, and remember this is a product, so you have to apply product rule. So e to the lambda t, the derivative of that is lambda times e to the lambda t times cosine of mu t. So that's the first part of the product rule. Then you add it with the first functions multiply with the derivative of the second functions. In this case, the second function is cosine of mu t. The derivative of that is going to be negative mu times sine of mu t. So that's just y1 prime. Now for y2, you have e to the lambda t times sine of mu t. And you take the derivative of this for y2 prime and apply a product rule. You have lambda times e to the lambda t times sine of mu t plus plus e to the lambda t times mu times cosine of mu t. And then you can use the formula for the 2 by 2 determinant to calculate the Wronskian at this point. So what you can do is that the product of the main diagonal subtract the product of the off diagonal. So you have e to the lambda t times cosine of mu t times e to the lambda t times psi of mu t plus e to the lambda t times mu times cosine of mu t. So this is just the product between this term and this term. Then you subtract e to the lambda t times psi of mu t, multiply with lambda times e to the lambda t times cosine of mu t, minus e to the lambda t times mu times psi of mu t. You have a negative sign here because in the derivative you have a negative pop-up from the derivative of cosine. Then you distribute and combine like terms and see what you get. Right? There should be some cancellations here. So I'm going to distribute, or first I'm going to take e to the lambda t as the common factor. I pull that out to make it look a little bit more, is easier to look at. So e to the lambda t, you have e to the 2 lambda t. So e to the 1 lambda t combined with another e to the lambda t, you have e to the 2 lambda t times cosine of mu t times psi of mu t. So lambda times psi of mu t plus mu times cosine of mu t minus, so we're going to do the same thing for this term. So pull out e to the lambda t. You got e to the 2 lambda t times psi of mu t, multiply with lambda times cosine of mu t minus mu times psi of mu t. Then you distribute and combine like terms. Okay, so the first distribution here is that you have e to the 2 lambda t times cosine of mu t times lambda times psi of mu t plus e to the 2 lambda t times mu times cosine square of mu t. Next, we're going to distribute this term into the bracket. You get negative e to the 2 lambda t times lambda times psi of mu t times cosine of mu t, and then plus, because negative with negative become positive, e to the 2 lambda t times mu times psi square of mu t. Okay, so you can do some cancellations here. So these two terms are the opposite of one another, so I cancel them out. And here I got that e to the lambda t, e to the 2 lambda t times mu times cosine square of mu t plus e to the 2 lambda t times mu times psi square of mu t. So you take e to the lambda 2, e to the 2 lambda t and mu as a common factor. So e to the 2 lambda t times mu give you cosine square of mu t plus psi square of mu t. And again, this is a identity, and that is equal to 1. So the Wronskian y1, y2 is equal to e to the 2 lambda t times mu. So in this particular example, there's no specific value for lambda and mu. So therefore, we show that the Wronskian is equal to something, but to ensure that the functions give you the fundamental set of solutions, we can show that for this Wronskian to be different from 0, mu has to be different from 0. Right? So this implies that to ensure that w is different from 0, we need to set or to assume that mu is different from 0. Because if mu is equal to 0, then this term is going to be equal to 0 as well. So w is equal to 0 to show that it's not going to be able to form fundamental set of solutions. Okay, so to ensure that w is different from 0, we need to assume that mu is different from 0. So maybe the conditions that lambda is different from 0 is a little bit redundant. Because when lambda is equal to 0, e to the 0 is equal to 1, it's still possible to have the Wronskian different from 0 when you assume that mu is different from 0. So there are just one conditions that we need to care here, that is mu is different from 0. Alright, so I'm going to move on to the last example in this lecture, example 5. So given the differential equations and the initial conditions, we are given another information that is y1 and y2 are the solutions of the initial value problems. Okay, so in this case where you notice that this is the second order differential equations, therefore you require to have two initial conditions. All right. And because of that, you have originally two solutions. But also, this problem wants to show that the linear combinations of the two original solutions can also be a solution to initial value problem. So this problem is, or this example is to illustrate one of the theorem earlier, that is, not only you have the solutions y1 and y2, the linear combinations of those two solutions is also a solution to the differential equations, or in this case, the initial value problem. So let's do that. So first, you need to check that the linear combinations or this particular function satisfy the differential equations. Then we're going to show that the function satisfy the two initial conditions. Okay, so let's do that. So given y of t equal to 1/2 e to the t plus 3/2 e to the negative t, the first derivative is going to be 1/2 e to the t minus 3/2 e to the negative t, and y double prime of t is 1/2 e to the t plus 3/2 e to the negative t. Then you substitute this value into the differential equations. Given y double prime minus y, we get that 1/2 e to the t plus 3/2 e to the negative t minus 1/2 e to the t plus 3/2 e to the negative t. So this part of those expressions is for y double prime, and this part is for y. So we plug them in these expressions, and they cancel out, and you get 0, which is a true statement here. So this say that the function satisfies the differential equations. So this shows that the function y of t satisfy the differential equations. Now the next step is to show that the function also satisfies the initial conditions. Okay, so y of 0, that is 1/2 e to the 0 plus 3/2 e to the 0. This give me 1/2 plus 3/2, give you 4/2 or 2 for that matter. And this is also a true statement. So indicate that the function y of t satisfied the first initial conditions. Now for the second initial conditions, you have y prime of 0 equal to -1. So let's see if the function satisfies the second initial conditions or not. So y prime of 0, that is, we're going to take this functions right here and let t equal to 0. So 1/2 e to the 0 minus 3/2 e to the 0. This give me 1/2 minus 3/2, or -2/2, or this is equal to -1. So it's satisfying the second conditions as well. So you conclude that the functions also satisfies the initial conditions. Thus, y of t equal to 1/2 e to the t plus 3/2 e to the negative t is the solution to the initial value problem. Okay. So that's wrap up lecture 8. So in this lecture, we briefly talk about the second order differential equations, and we have some example related to that to show that the given function satisfy the second order differential equations or not. We want to make sure that the solutions given are linearly independent and can form a fundamental set of solutions. And to do that, we need to calculate the Wronskian, and the Wronskian, if the Wronskian is different from 0, then the functions the solutions are linearly independent and they form a fundamental set of solutions. In addition to that, not only these functions given are the solutions to the differential equations, the linear combinations of those functions also are solutions to the differential equations. So that's it for lecture 8. Now I'm going to move on to lecture 9 when we dive into the first solution method to solve for this for the second order differential equations, specifically for the homogeneous second order differential equations. Okay.